Here are the solutions to homework set number 6 for ECE 320. The first problem, we're looking at a half H-bridge. For a full H-bridge, what you'd have is this circuit repeated, the other half of the 50 ohms, making 100 ohms, and another PNP, and another NPN going down like this, so that the current can flow left to right when these two are turned on, can flow right to left when these two are turned on, and otherwise. We're just looking at a half H bridge, just to simplify things a little bit. With a half H bridge, I've got three different conditions. I can turn on the PNP, making the output 5 volts, the NPN, making it 0 volts, turn them both off, so it's floating. Or, I guess that's it. So this is looking at those three cases. The first case is if I apply 0 volts at the input, there's no voltage across this diode, no current flow, means that transistor's off. I've got potential across this diode, it turns on, so probably this is saturated. When it's saturated, I have a 0.2 volt drop across the transistor. Makes this 4.8 volts. And for the currents, I've got 5 minus 0.7 over 0. 4.3 volts over 1K gives you 4.3 milliamps. 4.8 versus 2.5. 2.3 volts over 50 ohms gives me 56 milliamps flowing right. So that's the first case. I've got 4.8 volts here, current flows right. And the second case, when these are 5 volts, then there's no potential across this diode, that transistor turns off. I've got 5 volts across this diode, it turns on, and I've got 4.3 milliamps at the base. If beta is 100, milliamps to flow. I am only trying to push 46 milliamps this way. So 2.5 minus 0.2, 2.3 volts at 50 ohms is 46 milliamps flowing right to left, or minus 46 milliamps flowing to the right. So that's kind of the point. I have either plus current or a minus current. And there's a third case. If I turn everybody off, there's no voltage across this diode, it turns off. No voltage across this diode, it turns off. I'm floating. And the point behind the 2.5 volt source is when you're floating, I'll have 2.5 volts and 0 milliamps. If I leave this open, I have 0, and it's kind of hard to tell the difference between 0 and 0.2. 2.5 and 0 is a lot easier to tell. So I kind of have three logic levels. I can either make the voltage at V3 plus 4.8 volts. I can make it 2.5 volts or 0.2 volts. Three logic levels. In Circuit Lab, I can check the answers. You build the circuit, apply voltage at these two, and here's what I should get, 0.2, 4.8, 2.5. Here's what I actually got, 0.08, 4.88, 2.5. All it says is that when I saturate the transistor, it's roughly 0.2 volts when saturated. In this case, it's actually 0.08 volts, closer to 0. It's actually better than I expect. Instead of being 0.2 volts, this is 0.136 volts. Again, a little bit better than I expect. And 2.5 is 2.5. Now, kind of one sidelight from a practical standpoint, you want two separate power supplies for the two. What I don't want to do is get rid of this power supply and power it this way. The reason being is if I turn off the power supply and disconnect it, I now have a path to ground through both transistors. They both turn on and they just short a power to ground. That's how you burn out an H-bridge. You want both power supplies to be powered with separate power supplies so that there's no chance of current flowing from Q2 into Q1. In lab, the trick is now build it. So here's my half H bridge. Here's my 5 volt rail. Zoom in a little bit on that. So there's my 5 volt rail. Here's my 0 volt rail. Here's my two transistors, the NPN, PNP. Apply voltage at them. You basically boot the wires up and down, whether it's 5 volts or 0 volts. And what I get is when it's supposed to be 0 volts, I'm getting 0.09. Again, we're assuming 0.2 ballpark when the NPN's turned on. At 5 volts, or 4.8 volts, I'm actually getting 4.96. Again, closer to ideal than I expect. When you build it in lab, the results are consistent. Again, I can turn on the NPN. Here the NPN is turned on. I can turn on the PNP, and they're both off. So that's an H-bridge. And typical in this class, I've got the same circuit with 3 different answers. I've got what I calculated, what I simulated, what I measured. They're all different. They're close, they're consistent, but different. That's just because when you calculate, we're using an ideal diode model. Diodes aren't ideal. Simulated uses a more accurate model. That's still just a model, slightly inaccurate. The acid test is what does it really do? Circuit lab is closer than the ideal diode model. This is really what you want. So that's problem number 3. On problem 4. Problem 4 looks at an AC to DC converter. And here the idea, I've got a switch. If I close the switch, I have 20 volts right here. And V2 becomes some percentage of 20, like 19.5 volts. If the switch is open, this becomes 0 volts, and V2 becomes 0. As I chatter the switch, I can get any voltage at V2 between 0 and 20-ish, 0 and 19.5-ish. That's what this guy does. The purpose of the inductor is to serve as a low-pass filter. At DC, this has no effect. At AC, I have voltage division. Say this is 300 ohms AC. This reduces the ripple by a factor of 3. This reduces the ripple even more. If this is 20 ohms, that's 1/5 of 100. That reduces the ripple by 80%. So there's the circuit. To analyze it, what you do is you calculate what's the voltage at V1, both DC and AC, and what V1 is going to look like, it's going to look like this. When the switch is closed, I have 20 volts, because it's connected to 20 volts. When the switch is open, this is 0 volts, this is a 0.7 volt drop. So when the switch is open, I'm at minus 0.7-ish. The DC is the percentage weighted average. So if I'm 65% duty cycle, it's 20 volts 65% of the time, minus 0.7 volts 35% of the time. So there's the DC voltage at V1, 12.75 volts. Then the DC voltage at V2 is just voltage division. 100 over 100 plus 5 times 12.75. This should be 12.14 volts DC. Now for AC, let's do the AC in pink. AC, roughly the AC voltage is that distance. This is 20.7 volts peak to peak. And the units are important. There's peak, peak to peak, and RMS. We're using peak to peak units. So this is 20.7 volts peak to peak. The inductance becomes J omega L. That is J314. And this is 6280 times 0.05 gives you J314 ohms plus 5. The capacitor, what is the capacitor? Is 1 over J omega L. Let's work that out. So it's 6280 radians per second. That's omega. C is 5 microfarads, 5e minus 6. Whenever that, this is minus J 31.8 ohms. 20. There's minus J complex. So there's the capacitor. And parallel with 100, so take 1 over x, 100, inverse, add, inverse. In parallel, the inverse is add. So in parallel, this is 9.2 minus J 28.9. So by voltage division, it's what I'm measuring divided by the total, that plus this, times the input, times 20.7 volts peak to peak. So trying that, enter, enter, 5, enter, 314, complex, plus slash, times 20.7. Take the magnitude, catalog, function, absolute. This should be 2.2 volts peak to peak AC. So that's what I expect for V2. If I simulate in Circuit Lab what the PWM does, I have this go 0 to 10 volts. So 0 volts is 0% PWM, 10 volts is 100%. I want this to be 65% duty cycle, so this is 6.5 volts. That makes this 65% duty cycle. That feeds the base, that turns on the NPN 65% of the time. When this is on, that turns on the PNP. And when this is on, this is 20 volts. This is 19.8 volts. Again, you have a 0.2 volt drop across the transistor when saturated. When this turns off, the PNP turns off and the diode drives it. So running this circuit and doing time domain simulation, what I get, there's a figure, nope. I get the figure at V2. If I take the average, I get the DC signal. It's supposed to be 12.14 that I calculated. It's actually 12.05. The AC signal is 2.2 volts calculated, is actually 2.45. So I'm a little bit off. Again, the reason that I'm off is because I've got the square wave. I'm pretending that this is a sine wave with an amplitude of 20.7 volts peak to peak. That's not true, so my answer is slightly off. There are ways to get more accurate answers, the easiest being to use Circuit Lab. Harder ways, Fourier Transform, which is coming up in problem number 6. In addition, the DC voltage is a little bit off because the first transistor loses 0.2 volts. So when this is turned on, it's actually 19.8 volts, not 20 volts. And that affects my DC level. Problem 6. Change the duty cycle so that the output is 5 volts. Well, if V2 is 5 volts, then V1 has to be 5.25 volts. That's by voltage division. The duty cycle needs to be 28.74%. Again, I'm using 20 volts. It really should be 19.8, but I'll use 20. For AC analysis, 5 microfarads produce 2.58 volt peak-to-peak ripple. That's from the previous problem. Just scale it. If I make the capacitor twice as big, I'll have half the ripple. So to make the ripple 2.5 times smaller, make the capacitor 2.5 times bigger. So that'd be my guess on capacitor. Second approach is assume V2 is 1 volt peak to peak. That's going to be the resistor in parallel with the capacitor, which is assuming capacitor smaller than the resistor. Ignore that. Assuming this is much bigger than 1 over j omega c, it's roughly that. So it's roughly 1 over j omega c over J314. Solve, C should be 10 microfarads. Another way of doing it. Third way is just like we did before. Assume capacitor 0, calculate the ripple, see what percentage C should be relative to the output. Basically 10, 12 microfarads in there. If I try it, here's what the output looks like. Again, kind of notice it looks almost like a sine wave. That tells me that my assumption that it's just the first harmonic isn't that far off. When I design C, I designed for 1 volt peak to peak ripple. It's actually 0.85. I'm a little bit off. What I would do for second iteration, I'm 15% too low, so make the capacitor 15% smaller. Smaller C gives you bigger ripple. And the DC voltage is close, a little bit off, but again, fairly close. Again, that's probably due to the 0.2 volt drop across the transistor, the PNP. Last two problems. Now, in the analysis, our answers are wrong. The reason being is the input is a square wave, We're pretending it's a sine wave. A more accurate way to do it is use the Fourier transform. This is periodic, therefore it contains harmonics. I've got a DC term, first harmonic, second harmonic, and so on. So do that. Find the DC term, first input V0, and I'm going to use a little bit more accurate model. It's 19.8 volts, 65% of the time, minus 0.7, 35% of the time. C0 is the DC level, the average. C1 is the Fourier transform. It's twice the average of V0 hit with a cosine of j omega naught t. Here t goes for 1 second, because 1's a nice number. So the first harmonic's at 2 pi. Again, t is arbitrary. Seconds is not a universal constant. I just did a time scale, or a change in variable, so that the period is 1. 1's a nice number. Then the first harmonic is at 2 pi. Second harmonic is at 4 pi, 6 pi. So there's the first harmonic, second harmonic, third harmonic, 1 kilohertz, 2 kilohertz, 3 kilohertz. So this is what V1 is equal to, roughly. Now find V2. And this is using superposition. At DC, it's just a voltage division. Inductor, capacitor don't matter. There's V2 at DC. At 1 kilohertz, here's the frequency. Here's the capacitor. R2 is the capacitor in parallel with the resistor. R1 is 5 plus the inductor, j omega L. The output is R2 over R1 plus R2 times C1. There's the output at the first harmonic. Repeat at the second harmonic. Repeat at the third harmonic. When it's all said and done, combine them all together. I get the actual output. If you kind of notice, the second and third harmonic are small. If I ignore them, I'm pretty close, just including the DC term and the first harmonic. That says just including those two. The AC part is 2.46 volts peak to peak. Circuit Lab said 2.45. And notice that when you use Fourier transforms, the answers are really close. It's a lot of work, which is why we don't do it. But if you do use Fourier transforms, you do get the right answer. That also kind of leads to another approach. If I have a waveform that's not a sine wave like this, what I want to do is model that as a DC term and first harmonic. The DC term is same as before, take the average. The AC term, instead of saying it's this voltage peak to peak, what I should really do is find the first term in the Fourier series. Ignore the other terms, just take the first term in the Fourier series. That'll give you a better answer. For example, here, if I did that, I'm at 2.469 versus 2.45. Slightly more complicated, but a better way to do it. In terms of homeworks and tests, your pick. I like the peak to peak because it gives good intuition. I like the Fourier transform because it's more accurate. So take your pick. But anyway, that is homework set number 6 for ECE 320. Fourier transforms we're just introducing because if you're wondering why our answer is wrong, it's because we're doing it slightly incorrectly. It gives you good intuition, but slightly wrong answers. And in my book, if you want better answers, use Circuit Lab. When you get to signals and systems, you'll be spending like 3 or 4 weeks on Fourier transforms. So you'll see that again. That's probably the last time you'll see it in this class. So again, homework set number 6 for ECE 320.